Hi folks, this is the Unit 7 Day 5 video and we're going to be talking about concavity. This is the first video for Unit 7 Day 5. So in this video we're just going to kind of go over some of the big ideas and what concavity means and how we can use the second derivative to help us find out information that will give us more knowledge about what the shape of our graphs looks like and some other important points on the graphs. So the first thing is just to define what concavity means. Now, if a function is concave up, one of the kind of visual definitions of that is that the function is above all of the tangent lines on that interval. So these are both pieces of a function that would be concave up here or here, because the tangent lines, when you draw them in, are all below the function. The function is higher than the tangent lines. You also see kind of this upward shaped curve on both of these. If we were looking at concavity as to compare concave up and concave down, one thing I like to use as kind of a memory trick is that functions that are concave up look like they could be pieces of an opening up parabola. So the kind of most simple example of a concave up function is a parabola that's opening upwards. So if your interval or if your piece of a function looks like anything that might be kind of sort of a piece of this opening up parabola, then that would be a concave up section of your graph. The opposite of that, of course, is going to be concave down. So here would be pieces of functions or intervals on a certain function where it has a downward curve. Here, the definition visually is that the curve is below all of the tangent lines on that certain interval. And most functions, many functions, will have intervals where they're concave up and intervals where they're concave down. So we're just not talking about an entire function. Like for a parabola, that's kind of the simplest one. An opening down parabola is concave down all the time. But many functions, especially higher degree polynomial functions, will have intervals where they're sometimes concave up and sometimes concave down. And that's going to give us information about, obviously, the shapes of these graphs. So again, the concavity with concave down, the shape of that function can be compared to some piece of an opening down parabola. Not necessarily the turning point, but maybe these kind of endpoints you see like that. Anything that looks like it could be a piece of an opening down parabola, that would be a concave down segment or interval on your function. The next important definition here is a point of inflection. And you guys saw these a little bit when you were looking at polynomial functions in advanced functions. We talked then about when you had a triple root. So if you had, say, x minus 2 all cubed, that would have kind of an inflection or turning, not turning point, but kind of a point where the graph didn't go from increasing to decreasing, but kind of changed shape a little bit. And that's what we're finding here, but they're not necessarily on those zeros anymore. So a turning point is somewhere where it goes from concave down to concave up or concave up to concave down. So you can see this piece here looks like an opening down parabola. So this is going from concave down to concave up, and the point where that changes is the inflection point or point of inflection. And here it's concave up. That looks like an opening up parabola to concave down. And again, wherever it changes concavity, that will be a point of inflection. So what are we going to do to test for concavity? This is going to deal with the second derivative. And concavity, or changing the changing shape here of the slopes of the tangents, is sort of similar to the acceleration, how that describes the velocity. How is the velocity changing? Remember, velocity was slope of the tangent line, and acceleration described changes in that. So this is going to be looking at the concavity using the second derivative. So it's not how is the function changing, it's how is the slope of the tangent changing. So we're analyzing the derivative of the derivative. And if that second derivative is positive, then it's concave up. And I'll go back to those original graphs and kind of explain this a bit. If the function is negative, then it's concave down. If the second derivative is negative, it's concave down. And wherever the second derivative changes sign, that will be a point of inflection. So remember that we talked about the first derivative changing sign to find maximum and minimum points, and we had to find critical numbers where the first derivative equaled 0 or didn't exist. Those are going to be the same things that we find to check for a point of inflection, where the second derivative equals 0 or does not exist. And I just want to go back a little bit to talk about this. Now, if we look at the first derivative here, f prime at x, so the slope of the tangent at, say, this point here is large negative, and moving along as x gets bigger, here the slope of the tangent is a small negative. So it went from a larger negative slope to a smaller negative slope. And this means that f prime at x is increasing. So when the derivative is increasing, that means that the second derivative is greater than 0. So for this piece where it's concave up, it goes from a big negative, like maybe that slope is negative 10 and that slope is negative 1/2. So negative 10 going to negative 1/2, you're getting bigger. So your derivative has increased. That means the second derivative, the rate of change of the derivative, is positive. And here, kind of the opposite, this slope here is small positive, and here the first derivative is large positive. So what's the rate of change of the derivative? How is the derivative changing? It's going from a small positive to a large positive. That means f prime at x is increasing. If the derivative is increasing, then the second derivative, the derivative of that derivative, has to be positive, because my derivative function is increasing. The derivative of that derivative, which is, that's a lot of times to say derivative, but that's the second derivative, will be greater than 0. And sort of the opposite situation here, if we compare these ones, so here we've got f prime at x is, this would be a large positive. So the slope there is big positive, and here the slope is big negative, or small positive, pardon me. So here we've gone from a big positive number to a small positive number. So f prime at x is decreasing. So that means the rate of change is negative. F double prime at x is less than 0 because the derivative is decreasing. The second derivative is negative. Here, kind of again the opposite. This is going to have f prime at x is small negative. And here, f prime at x is big negative. So that means, going from there to there, f prime at x is again decreasing. So the second derivative is negative because the derivative function is decreasing. That means the second derivative is negative. So that's just kind of the, I guess, visual or geometric graphical representation of why we can do that second derivative test, checking whether it's positive or negative. So really it's going to feel very similar to how you find intervals of increase and decrease and whether something's a max min. We're just doing the same kind of analysis with the second derivative now, and we're going to be looking at where the second derivative is positive or negative for intervals of concave up, concave down, and where it changes sign for a point of inflection. We're going to test, again, very, very similar to your critical numbers with the first derivative. We're going to test where the second derivative equals 0. These are potential points of inflection. Or where it does not exist. So we're looking for does not exist or equals 0, but now from the second derivative. If the concavity changes on either side of these points, then P is a point of inflection, assuming F at P exists. Sometimes a function can change concavity around an asymptote, and then that's just a change in concavity, but because the point is not defined on your function, it's not going to be a point of inflection because there's a restriction there. And you'll see what I mean in the second example for that. The second derivative can also be helpful looking back at max min values. So now that we kind of know some stuff about concavity, this is an easy way to test for the maximum if a critical number is a maximum or a minimum. So if you find a critical number, and we've been testing the table to look at does it go from increasing to decreasing, you can also say if this is a critical number, that point there, and it's concave up, then a concave up with a derivative of 0, first derivative of 0, means that that has to be a minimum, because if your first derivative is 0, the function is all above the tangent line where it's concave up, so that would have to meet it at a minimum. Okay, so here, this first derivative equals 0, and the second derivative is positive, telling us that this is a concave up shape. So we know we have a horizontal tangent, and we know that the shape of the graph is concave up, so it can't be going like that. This doesn't work for all critical numbers. It doesn't work for places where the derivative doesn't exist. So remember, we had to test the zeros and the points where the derivative doesn't exist. So it doesn't work for everything, but it can work in a lot of cases. The opposite of this here, we have the first derivative again equaling 0. And if the second derivative at that point is negative, we know it's concave down there. So the tangent is above the function must be below that and have a maximum at that point. Another case where the second derivative test doesn't work, and this is optional, you don't need to use this at all. You can keep using the table, but it can be a little bit shorter if you kind of get the hang of using this. Here I have a horizontal tangent, so the first derivative equals 0, but it's actually not a turning point at all, because the second derivative also equals 0. So sometimes those critical numbers are not going to be turning points. They might be an inflection point, or they might be neither. You have to kind of analyze the signs around that point in the table for this type of situation. So sometimes it works, and sometimes it's a little bit of a shortcut in determining whether something's a max or a min.